Hi, my name is Brian Suchy, and today I'm going to talk about Carrot Cake, or our attempt at replacing paging via compiler and kernel cooperation. And let me summarize the talk before we jump in. In this talk, we claim that the current model for memory management via paging is becoming unsustainable, and the motivations for its creation are losing their strength. We then introduce the concept of CARAT, or compiler and runtime-based address translation, a software-only memory management system to address some of these shortcomings. We then dive deeper and bake a full system implementation from the kernel up called Carrot Cake, or CARAT for collaborative kernel environments, that runs using CARAT as the memory management scheme. After showing that CARAT is competitive with current memory management systems, we explain new benefits that CARAT provides that traditional systems are unable to. And here's an overview of how the rest of the talk is going to go. So let's start with a bit of background and motivation. Paging and virtual memory was introduced at a time when memory was counted by tens of thousands of words. Virtual memory enabled programmers to treat memory effectively as unlimited. However, today memory is now counted in gigabytes or even terabytes, meaning for most programs, they effectively do have unlimited memory. But because virtual memory and paging became the basis for memory management, the supporting hardware has tried to adapt to keep pace with the changing environment. Unfortunately, data footprints continue to grow while the TLB still only has a reach of 3 gigabytes, and the hit rates are no longer in the upper 90 percentile. Additionally, this hardware supporting virtual memory today requires 15% of on-chip power and takes up as much space as an L1 cache. However, one change in today's computing environment is that software systems are much more sophisticated and involved. Operating systems have become significantly more complex and rich, and compilers are significantly more integral, which in turn enables them to take a much larger role in computing. So with the changing landscape of computing, why not try and make memory management systems completely in software? Doing this would allow us to circumvent the hardware's energy, area, and hit rate problems that are beginning to rise altogether. Additionally, a software-only system would afford us new directions to improve the system as a whole. And that is exactly what we began to do with CARAT, or compiler and runtime-based address translation. Let me explain what CARAT is by showing what it looks like from a process perspective. This is the traditional address translation model. A notable feature is that the hardware is complex and uses virtual and physical addresses in its execution. The TLB and PageWalker are integral parts to ensuring that the translation from virtual to physical addresses works seamlessly for the user. But this again comes at a 15% power overhead, as well as being on the critical path for execution. The idea for CARAT is to remove this complex hardware and addressing scheme in favor of a simpler alternative. The CARAT model can operate with only physical addresses, making the hardware simpler, more energy efficient, and in many cases faster, and it does so by making two changes in software. The first is a set of compiler passes that will inject code to track and protect memory. The second is linking programs with the CARAT runtime and signing the binary. The runtime will keep track of memory, as well as enforce protection directed by the compiler. The signing of the binary verifies the program was produced by CARAT's toolchain. This results in a binary that works cooperatively with the kernel to implement functions originally provided by virtual memory, but now using only physical addresses. Now let's look at a simplified example of how the compile side transforms a program. In this simple C program, we see that we have a few globals, mallocs, and some memory operations. The first transform we make is the allocation and escape tracking, which intends to track all allocations and escaping pointer references a program makes. The things we need to track are the globals made on lines 1 and 2, the malloc on line 9, and the escaping pointer reference on line 25. The transform locates all globals and adds tracking code to the beginning of the program before the first initial instruction runs. For mallocs and escapes, we add tracking code after their operations. The next transformation seeks to guard all memory accesses. A guard ensures that the program has permission to access that specific piece of memory. Let's take the two memory accesses on lines 18 and 21 as examples. As we can see, our transform places guards before both of these memory accesses in the loop. And compiler analysis can also reduce the overhead that these guards introduce. For line 18, the compiler can recognize that the accesses correspond to the induction variable I. And using this knowledge at compile time, the transform can instead hoist the guard out of the loop and verify the entire array before running the loop, which saves large amounts of time. So, is a CARAT-like system feasible? The first attempt at answering this question resulted in observing that the overhead of a CARAT system was only 9%. And note that this was while running as a user-level prototype on top of paging. Because the system only emulated what a CARAT system might look like, the next natural question is, what would an actual system look like? Which brings us to, baking a carrot cake, our creation of a full system implementation of CARAT from the kernel up. So what is carrot cake? Carrot cake, or CARAT for collaborative kernel environments, is a CARAT-based kernel that can run Linux processes. Running with CARAT as its memory management system means that it can run without any support from the TLB, paging, or any other virtual memory construct. So let's put on our chef's hats and start baking this carrot cake. And so let's start with the base layer of the cake, the Nautilus kernel. The Nautilus kernel serves as the base in which we can add everything else to in order to bake the carrot cake. Nautilus is a research kernel developed at Northwestern, and the main reason for picking Nautilus is that it offers a bare bones memory management system based on huge page identity mapping that can be built upon to allow carrot cake to truly be built from the ground up. And now that we have a kernel and a bare bones memory management system to build on, let's start by adding in a new address space abstraction. And we implemented an address space abstraction that would be compatible with both paging and with CARAT. To accomplish this, the abstraction is comprised of two generalized parts, memory regions and thread membership. A memory region in an ASpace is a base unit at which one can assign access permissions as well as map available memory to a process. For paging, these are pages. For CARAT, this can be many things, including but not limited to pages, mmap regions, numazones, individual allocations, or even arbitrary lengths of bytes. Thread membership keeps track of what threads are affiliated with an address space. Interactions with threads occur when entering, exiting, or changing an ASpace. For paging, the threads need updates to their page table pointer when switching between ASpaces. For CARAT, the threads have an expanded role. On top of updating their context, the threads can also have their registers and stacks manipulated to accommodate updating memory. So let me explain a bit on how the compiler-injected calls from the example interact with the carrot cake ASpace. One new data structure in a CARAT ASpace is the allocation table. The allocations and escapes tracking instructions populate this data structure. The allocation table keeps track of all allocations as well as metadata about those allocations, such as those escaping pointer references or escapes. The other important data structure in a CARAT ASpace implementation is the region map, which interacts with the guard injections. The region map keeps track of all memory regions, which contains access permissions in an ASpace. Note that if a system wants to manage memory at allocation granularity, the region map and the allocation table can be the same data structure, as each memory region has a one-to-one mapping with individual allocations. Now let's dive a bit deeper on how the guard injection pass interacts with the CARAT ASpace. Whenever a guard is injected by the compiler due to a memory access, it does a lookup in the ASpace's region map to verify the access permissions and existence of a memory region. Assuming that the access is allowed and the region exists, the ASpace returns and allows the program to continue running. If not, this is the point that the kernel is invoked to handle the failure appropriately. There are a few optimizations made to this guard to make it more performant. Firstly, like in the example earlier, the compiler can be used to reduce the overhead. The compilation optimizations are more detailed in the paper, but they focus on essentially removing redundant checks whenever possible. At runtime, we use hierarchical checking of memory regions, such as checking the user's stack and heap memory regions first before going to the region map. With an ASpace cooking, we can now add in the Linux Syscall interface as the next part of the cake layer. Known to us as the untrusted front door, the Linux Syscall interface adds in compatibility for Linux syscalls and signals for programs that are expected to run on a Linux system instead of Nautilus. Some things to note with our implementation is that the syscalls execute in the same address space and permission level as the executing program, which requires some care and implementation further described in the paper. The syscall interface currently has added support for most of the important calls in the C runtime and library allocators, as well as signals, with a focus on supporting the benchmarks later on. With the Linux syscall interface added, we can now talk about the next part of the cake layer, the allocator and defragmenter. Allocators in a carrot cake system would ideally be designed with the assumption of CARAT address spaces running underneath them, but this is not a necessity. For the evaluations later on, we're going to use the libc allocator, which does not assume carrot cake, and this will eventually allow us to directly compare to paging. And using carrot cake's defragmenter, we enable the ability to defragment all of the memory on a machine in a hierarchical manner. The kernel can first defragment individual allocations or all allocations in a single memory region of a single CARAT ASpace. A step up then allows defragmenting some or all regions of an ASpace. Finally, the kernel can decide to defragment some or all of the existing A spaces, which defragments all of the system's memory. Another thing to note is that the kernel is not limited to defragmenting processes it creates, but the kernel can also defragment and move around itself. And now that we can add the final ingredient of this carrot cake layer, which is the trusted hooks implementation. Known to us as the trusted backdoor, this is where the compiler injected calls can access the kernel. When creating a process for a carrot cake system to run, the kernel creates a function data table inside the program. The compiler then injects calls to access this table rather than directly accessing the kernel. Upon finishing compilation, the compiler signs the binary created. And when it's time to run the process on a carrot cake system, the loader verifies the compiler signature and upon verification, actually populates the data table with the functions for performing protection and tracking. The middle layer of our cake is now completed, which allows us to add the top layer of the cake, the Linux compatible process, or LCP. The LCP layer abstraction allows us to run and separately compile programs onto Nautilus as if they were running on Linux. The LCP does so by using the layers below it to offer the processes all the things that a typical Linux process would expect and be limited to, all while operating using CARAT as its underlying memory management scheme. And at this point, we've added all the ingredients and fully baked our carrot cake. So now it's time to evaluate our carrot cake, which brings us to the bake-off evaluation of carrot cake. Before evaluating, let me give some background on what we use to evaluate carrot cake. For the testbed, we ran carrot cake on an Intel Xeon Phi Knights Landing processor with 96 gigabytes of DRAM. And using this testbed, the benchmarks were from the NOS benchmark suite, as well as the Parsec benchmark suite. And finally, the competitors in the bake-off include carrot cake, a modern paging implementation on Nautilus, and paging on Linux so that we can normalize them to one another. So our carrot cake was evaluated in three primary ways. The benchmark overheads, which seek to answer the question of how the overhead of a carrot system looks like compared to paging in steady state operation. A memory movement stress test, which seek to answer what carrot overhead looked like in a state of constant memory movement. And finally, an engineering effort, which gives some insight into engineering effort required to implement carrot in a kernel. So let's start with benchmark overheads. The overheads being reported is all normalized to paging on Linux. The results from running these benchmarks indicate that carrot only has a 1.8% overhead when comparing to paging on Nautilus. And out of all of the benchmarks, the worst case overhead we saw with carrot cake was being 16% slower than paging on Nautilus. However, in some cases, carrot cake actually performs faster than paging despite having the calls to track and protect memory via software. The main takeaway from this is that the overhead using carrot cake makes it a competitive alternative to the current paging implementation on machines. And another key thing to note with this evaluation is that there are other benefits that would even make this better. And I'll discuss those later on near the end. And these would definitely benefit carrot cake, but not paging. The next step of evaluating our cake is how it performs during high memory activity periods. The memory movement in carrot will be more prevalent in a carrot system as any updates to the memory requires potential data movement. To measure how this will impact carrot cake, we created what we call the pepper test. The pepper test creates a very pointer-dense segment of memory and continually moves it around during execution of a program. And the denser a piece of memory, it means that carrot will need to do more work to move it. We can then vary the size of this data structure as well as the memory movement rate to form a model on the overhead expected from putting carrot cake under constant moving conditions. And a quick note on pointer sparsity and density. Pointer density is a measure of how many bytes in a memory region exist per pointer in the memory region. A denser, or rather less sparse region, is more difficult to move as it requires carrot cake to perform more work in updating escapes per amount of memory being moved. For example, a linked list with only the next pointer inside each node is a maximally pointer-dense structure, as each byte in the data structure is used for pointers. And this is the worst case data structure to move in the pepper test, which is why we used it. The benchmarks in the Nautilus kernel in this paper display sparsity orders of magnitude more than a linked list. And therefore, the results of this test are better when moving things like programs or the kernel. So let's look at the results of our test. We observed that carrot can handle quite a high amount of memory movement on a system. And to give some context, our prior work states that the actual expected movement rates on a carrot system would be somewhere in the 0.1 hertz range. And running at those rates, we see that we experience virtually no overhead when moving around a 100,000 node linked list. Additionally, when moving at a rate 10 times the expected rate, so 1 Hertz, we can still move 10,000 nodes with no observable overhead. And in the paper, we provide a model that gives more rates and the expected overhead. But in summary, the results were very promising with CARAT and showed that it was very feasible. The final test we had for evaluating CARAT was the engineering effort involved in creating Carrot Cake. Creating Carrot Cake did involve more engineering effort than paging, and we broke down the extra work by sections. The first section involves the extra work on the compiler side. The allocation and escape tracking compiler passes involved roughly 2,000 more lines of code compared to paging, and the protection pass adding on 1,500 more lines of code. The linking and signing of the binary added an additional 50 lines. On the kernel side, Carrot Cake needed roughly 800 more lines of code compared to implementing paging. Again, note that the paging implementation is a modern implementation that makes use of large and huge pages, as well as process context identifiers. Finally, Carrot Cake makes much more extensive use of compiler optimizations and tools not created by our team, such as WLLVM and Noel, which are open source third-party tools. And on the flip side, we want to note that for the architecture, Carrot Cake no longer needs the hardware for address translation, and therefore that hardware no longer needs architectural support or development. And this brings us to the wrap-up portion of our talk. In the wrap-up, I want to touch on some of the benefits realized by using Carrot Cake that are not available when using paging. Firstly, we are no longer reliant on address translation hardware. This means that we can save 15% of on-chip power if we simply power off this hardware, or additionally, we can save area the size of an L1 cache if we simply remove the hardware altogether. Another benefit is that we no longer need to couple virtual memory with cache design, allowing us to expand L1 caches up to 4 times their current size while maintaining the same energy and timing requirements. The previous 2 benefits were not realized in this paper. However, the system did make use of allowing memory to be managed at an arbitrary granularity. Additionally, the benefit of software improvements making the system faster was also seen by us from the benchmark overheads improving. From the original paper, we improved from a geomean of 9% to 1.7% for steady state overhead. This was done through compiler alias analysis improvements, as well as implementing CARAT in the kernel instead of as that user level prototype built on top of paging. So just to recap everything, we claim that the traditional model of memory management is starting to become unsustainable. And to address this, we used modern compilers and system software to implement a feasible software-only memory management system from the kernel up. We then evaluated the system against a modern paging abstraction and determined that we are a feasible alternative today. And when using this model, we highlighted some brand new opportunities that are now enabled. I'd like to thank you all for listening to my talk. And if you have any questions, feel free to email me at brian@briansuchy.com. Thank you.